charla pueden también hacerlo con la misma función de levantar la mano y ya yo les cedo la palabra y cuando pueda encontrar un momento para interrumpir a Benjamín. Y si no, al final también tenemos la sesión de preguntas y respuestas al final, como siempre, ¿vale? Entonces, bueno, les recuerdo que este es un coloquio dentro de nuestra jornada de celebración del 60 aniversario, que bueno, lo cumplimos hace un mes por ahí, el 60 aniversario del centro y del departamento, al ser uno de los departamentos fundadores. Bueno, entonces, con esto decidimos invitar a algunos, bueno, graduados o que forman parte de la historia del CINVESTAF. En este caso tenemos el honor de tener con nosotros al doctor Benjamín Grinstein. Él es actualmente profesor del Departamento de Física de la Universidad de California en San Diego. Inició sus estudios de licenciatura en Ingeniería Biomédica por un par de años en la Universidad Iberoamericana, pero antes de graduarse ingresó a la maestría en Física en nuestro departamento, porque en ese momento con que pasaras los propedéuticos, y entonces él tomó ese gran reto bastante joven antes de terminar la licenciatura sin haber estudiado nada de física, de licenciatura en física. Entonces ingresó a nuestro departamento del 78 al 80 y luego hizo su doctorado en física en Harvard del 80 al 84. Luego trabajó en varias instituciones como postdoc, como profesor asistente, como profesor asociado, entre ellas Caltech, los laboratorios Lawrence Berkeley, el Laboratorio Nacional Fermi y la Universidad de Harvard, antes de ingresar a la Universidad de California en 1994. Bueno, por si no lo conocen, bueno, según Google Scholar, el doctor Grinstein tiene más de 22,000 citas y un índice H de 73, que bueno, que saben lo que significa ese número. Ha recibido numerosos premios y reconocimientos por varias instituciones como Harvard, Caltech, la American Physical Society y la Sociedad Mexicana de Física. Además fue editor de la revista Physical Review D y actualmente es editor de la Physics Letters V, que son para los que no lo sepan, son de las dos revistas más importantes del área de física de partículas. Y bueno, ahora le agradezco de nuevo a Benjamín que ha aceptado con nosotros y puede iniciar su charla. Adelante.
Pues, un placer por la invitación, muchas gracias, un placer estar con ustedes. David, me habías dicho que la plática en inglés, ¿verdad? Porque hay gente que...
Como tú quieras.
Y puedo hablar español muy bien para hablar de comida y de relaciones, pero hablar física se me hace muy difícil en español. Entonces, ¿me puedes dar permiso de presentar?
Voy.
Gracias.
Permítame que me metí en la incorrecta.
Bueno, mientras tanto, José... Ok, gracias. A ver si puedo hacer esto.
Ya lo vemos en modo de edición.
Aquí está, ok. Y ahora sí lo ven en pantalla completa.
Sí.
Ok, muchas gracias. Ok, voy a cambiar bueno, voy a darme una página más en español y luego me cambio al inglés. Bueno, me da mucho gusto, como dijiste, dar este coloquio en el 60 aniversario del Departamento de Física. Voy a hablar acerca de un tema que está a medio camino entre física de partículas y física nuclear, del que no soy nada de experto, pero está muy simpático y divertido, y la plática creo que es muy accesible a cualquier persona de cualquier campo. Quería mostrar que el trabajo lo hice con un muy buen postdoc, se llama Bart Fornal, que ahora es postdoc en Utah. Y una página nada más. Bueno, tú ya lo dijiste, que hice la maestría en el CINVESTAF del 78 al 80, y estaba tratando de buscar unas fotos, a ver si tenía algunas fotos de ese entonces para conmemorar el 60 aniversario, y desgraciadamente no pude encontrar nada. Creo que entonces, como no teníamos iPhones, no tomamos fotos, pero aquí hay una foto de Murad Alexania, que fue mi director de tesis. Mi tesis no fue en partículas, fue más con mecánica estadística. Y le debo mucho a Murat por todo lo que me enseñó. Pero también hubo mucha gente que tuvo un impacto muy grande en mi carrera, no solamente esos años, pero a futuro. Y aquí nombro algunos de ellos. Pero había muchos más, y entre aquellos otros estuvieron muchos de mis... los estudiantes que estaban al mismo tiempo que yo. Entonces veo las memorias con mucho cariño y espero poder regresar cuando se acabe la pandemia algún día a verlos a todos ustedes en persona. Okay, and now I'm going to switch into English. So let me tell you the story I want to tell you about. So I'm going to be talking about particles, and the particles I'm going to be talking about are particles that make up stable matter. So they're made out of quarks, like the up quark and the down quark, and those together with electron and neutrino make up the first family of elementary particles. And that's really all that I'm going to need as far as elementary particles in this talk is concerned. But it's worth remembering a little bit more about what we know. So we know that there's 4 fundamental forces, and I'm not going to go over them, but surely you're familiar with electromagnetic and gravitational forces. And to remind those of you who are not in particle physics, the weak force is, which I'm going to talk more about later, is responsible for beta decay or radioactivity, and the strong force binds the quarks together into nucleons. Now, in fact, the list of elementary particles is nice and compact, and it fits into this nice little chart. So the first column I showed you before. The second and third columns are kind of identical copies of the first as far as quantum numbers are concerned, but they just correspond to particles with higher masses. Then the fourth column, this column in red, and I guess I should get a pointer, which well, I can't remember how to do this to get a pointer.
Yesterday you did it on the pencil.
The pencil, right? Oh, laser pointer. Very good. Thank you, thank you, David. So the fourth column here is in one-to-one correspondence to the forces that I showed in the previous transparency, and shows the particles that mediate those forces. So the gluon for the strong force, the photon I don't have to tell you, and the Z and W bosons for weak forces. The graviton is not here because we kind of don't know how to include it if we include quantum mechanics. And then there's a particle we didn't talk about, which is the Higgs boson, but again, it's not going to play a role in my talk. But this is really the whole story, and this model is tremendously successful. If you ever seen the particle data book, it's not a very big, thick volume, and it explains with very high precision a huge number of processes and measurements. And there's a few deviations here and there, but you expect that even just from statistics. Of course, some of those deviations can get really interesting, and they may point to some failures of this model. And one of the challenges that we have is to try to disentangle what is noise from what is actual information about what else there may be beyond this model. The model is actually also very elegant. You can write the whole of the dynamics in terms of a Lagrangian that takes 4 lines. So this is enticing, and of course, this is a little bit of a fake, because if you write out explicitly what the symbols mean, you get a little bit more detail. And of course, you need that kind of detail if you're going to describe all these great variety of phenomena, the very long list that I described before. But the point is that the left box implies the right, in the sense that these are just very fundamental principles that lead you to write this. So these, together with the list of particles that I showed above, which is just some quantum numbers specified, leads automatically to the right side. And the proof that this must be the correct model is that you can now get MOGs which have it on it. So what else do you need for proof? Well, in fact, maybe not everything is correct, or at least not complete. There's a problem. There's a problem that we've known for many years, and work that started early, and Vera Rubin kind of made some of the most important discoveries in this regard, that the universe is made of about 30% of matter, but out of that 30%, 80% or so is matter that we don't understand, the dark matter. Now, this is not a colloquium about dark matter, and I'm not going to spend much time talking about the evidence for it and so on. So I hope you have heard about it elsewhere. But I will have a few things to say about it, and because of it, this work has received more attention than it would have if we didn't have something to say about dark matter. So dark matter is there. We know that because of its gravitational effects, but we don't know what it is. And then the question really has become, what is the nature of this dark matter? And so, the fact that matter makes a small fraction and of the matter of the universe, it's a little bit like the question of and you want to know what all of the matter is like. It's like it's a little bit like the question: I give you the chassis of a car, and you have to tell me what does the car look like. And we don't know, and there's a huge effort in the physics community to try to find the answer to this question. And it could be that the answer is something that looks like this, but until and you come up with a empirical result, a direct observation, or some at least better some kind of evidence of the nature of what the nature is of this dark matter, this could actually be something more like this. And so we're hoping that work like ours might be the key to answering this question. That would be, as I said, it's not the main focus, but it's been something that's been really enticing. So let me turn to the issue at hand again. To remind you all, I'm sure you know, the atomic nucleus is made of protons and neutrons, and the neutrons is made of quarks. The lifetime of the neutron is long. It's about 15 minutes. And if you wonder why it is that the atomic nucleus doesn't fall apart, it's because this lifetime is for a neutron in free space. But when you bind the neutron into a nucleus, there's an energy barrier. There's no phase space for the decay because the neutron is in the potential well of the atomic nucleus, and it cannot decay. Just kinematically, it's not allowed. So in the standard model, the decay proceeds. This is just beta decay. It's just the prototypical beta decay, is the decay of the neutron into a proton, an electron, and an antineutrino. And it's mediated by one of these particles that we call the W particle. So it's a gauge boson, which carries charge minus, and it is called the W boson, very creatively. And this Feynman diagram gives you a pictorial representation of what's happening when the decay occurs. So there's a few things that I want you to remember about particle decay, because we're going to be using them, particularly if you're not from in nuclear or particle physics. This might not be something that you think about all the time. So typically in particle decay, quantum numbers are conserved. So quantum numbers are exactly conserved in particle decay. the initial state has the same quantum numbers as the final state. And energy and momentum are quantum numbers that are exactly conserved. So the energy of the initial state and the momentum of the initial state are identical to the total energy and total momentum of the particles in the final state. This means that a particle can decay, has to decay into at least two particles. That just follows from momentum conservation. If you go to the rest frame of the decaying particle, that means that the resulting particle in decay has to have zero momentum, but it also has to have the same total energy as the initial particle, and that implies that if it is a single particle in the final state, it has identical mass as the initial particle, so there's no decay. So you need two particles in the final state. And finally, kind of the same statement that the sum of the final state particle masses should be smaller than the initial particle mass for the decay to proceed. And I'm going to be using that aspect of it. Well, something that you learned in kindergarten is that the decay rate follows an exponential. The rate of decay is proportional to the number of particles when you have a collection of particles that are decaying, and so this proportionality constant, of course, defines the lifetime. And so you can extract that proportionality constant by fitting to an exponential, or by going anywhere on this plot and getting the slope of the curve. From this slope, it's really the slope of the logarithmic derivative. You have to divide by n, gives you the this constant, which in turn gives you access to the lifetime. Okay. So that's the preamble. Now let me tell you what the issue is. This is a problem that has existed for many years, and it's become more and more pressing over time. And it's kind of a peculiar problem. This is a plot of the measurement of the neutron lifetime as a function of when the measurement was made. And that's just kind of differentiate the different kinds of measurements. The measurements in blue were made by a process, by a method that I will describe shortly, called the bottle measurement, or the bottle method. And the result of averaging all of these results is a little under 880 seconds. For the, as I said, the neutron lifetime is about 15 minutes, but I want to be a bit more precise now. You can see that these measurements have become more and more accurate over time. And this very latest result is what got me and Bart very interested. And I'll talk about this when I explain the bottle method for measurement the lifetime. Those in red are made with another, are measurements that are made with another methodology. These are made with the beam method. I will also explain that. And as you see, the average of these is different from the ones in blue. And in fact, I wrote on the right-hand side here one of the most recent averages for the beam separate from the bottle and experiments. And you see that there's a discrepancy between them, which is 4 sigma. You can actually compute this discrepancy. It turns out to be 4.0 sigma. So what you see by I is actually correct. And as far as the magnitude of the discrepancy, it's only a 1% effect. So I need this number 1%. But of course, what matters here is that it is significantly, it's very statistically significant. The last measurement here in this red point, which has very, very large error bars, is a measurement that's reported very preliminary results and is ongoing at a laboratory in Japan, and is eventually expected to give the best measurement of this beam type experiment, but has not been published yet, and probably will not for the rest of this year, maybe this year or later. Okay, so that's where we are. That's the puzzle. Why are these two measurements different? So let me explain what these measurements are, because they're pretty awesome, particularly the bottle experiment. The bottle experiment, I want to spend a little bit of time talking about it because it's like mind-boggling. What you do is you take, you make neutrons somehow, doesn't matter how, and you cool them off. It doesn't matter how, we can explain, I can talk about it later, but cooling off neutrons means making them very, very slow. So you can get a beam actually of neutrons that are barely moving. And by barely moving or cold, we mean that you can actually walk, if you walk fast or do a little jog, you can go faster than these neutrons, which is quite remarkable because at least almost any time you talk about elementary particles moving, we're talking about fractions of the speed of light. Here we're talking about meters per second type speeds. So you take these very cold neutrons and you collect them in a bottle. And what by a bottle, I really mean a bottle. I don't mean something very sophisticated. They are sophisticated bottles because they get special, covering of this or that material that tries to minimize absorption of the neutrons in the wall of the bottle. But think about it. If you look at the de Broglie wavelength of a very slow particle, the wavelength can be very large, much larger than the distance between atoms. And in fact, a slow neutron doesn't see individual atoms on the wall. It sees a very large collection of atoms. It sees a wall, very much like a photon would see a mirror. So, to do this more formally, you'd have to compute a Fermi potential of the whole surface and so on. But basically, these very slow neutrons just bounce off the walls of the bottle, and they can cool off as they bounce off the walls, and although it's not easy to cool them off then, but this gravitationally they just go to the bottom of the bottle. So literally, it's like a jar of milk or something. It's just sitting there. And so what you do in these experiments, this is literal. You take this bottle, and then after some time, you take the bottle and you tip it so that some neutrons come out, and you count how many neutrons come out. And if you do that at separate times, as this figure indicates, you can get the number of neutrons coming out of the bottle, and then plot that as a function of time and track the exponential. In fact, what's usually done is you can either take a bottle, fill it, and empty it at different times. So you can do this several times. And at what rate you're filling up the bottle, so you know that the amount of neutrons in the bottle that you start with is consistently the same, and you repeat it many times. Or in some cases, you can actually tip the bottle some, and then tip it some more, and tip it some more. In either case, you can trace this exponential. And then feeding to the exponential gives you the lifetime. So this is an awesome type of experiment. And then there's the beam experiment, and those of you who do particle physics are probably more familiar with this type of setup, in which you have a beam. Now it's not a cold beam, it's pretty hot actually. These things travel very fast through a tube of some sort, some container, always in high vacuum, of course. And as it goes through this tube, you have a region which is instrumented, so that neutrons that decay, that beta decay, can be detected. So what you detect is the protons that get emitted as the neutron decays. And this shows here a trap. These positive and negative signs indicate that the best way to do the detection of protons is to first trap them, so that any neutron decay produces a proton that gets trapped, and then you're attracted towards these negative electrodes that are instrumented. And this is important because you don't want to lose any protons in the measurement. Now, what happens here, of course, is that these things are moving very fast. So you're not seeing all of the neutrons that are decaying. You're seeing a fraction, delta n of the neutrons that decay in a distance delta x, if you want, corresponding to the size of this trap, which can be related to the time it spends in the trap. So you are really measuring is the rate of decay, the rate at which the protons are observed as a function of time. And then to get the lifetime, you have to normalize by the number of neutrons coming in. And this can be measured very, very carefully. So those are the two experiments. And since the neutron decays through proton decay, through beta decay, do you expect the beam lifetime and the bottle lifetime to be the same? But they're not. Now, of course, this could be an instrumental issue or a systematic issue. The experiments are done by many different groups, the ones that I showed. So somehow everybody's committing the same type of mistake. That's a possibility. But the fact is that we have this discrepancy in which the beam result is larger by 4 sigmas, I said 1%, than the bottle. So I'm not going to contemplate this possibility that these experiments have a systematic or that there's a statistical fluctuation. That's certainly possible, and that could just could resolve this. I'm going to assume that that's not the case and ask, what do we do then? And my track is going to be, well, can new physics explain the two different lifetimes? Yeah. There's a question? No? Okay. Well, let me know if there's a question. So can the new physics explain the two different lifetimes? And, because there's the expectation that maybe this gets resolved eventually just by instrumental issues, people have said, well, what is the point of this? And I claim it's not a pointless exercise. We want to formulate a hypothesis, we want to check that it is consistent, then we want to make predictions, and then we can test them. And I can tell you up front that that this attitude actually was initiated a number of experiments that have been very useful in trying to understand better what's going on. So that's why this is useful. But who knows? Maybe it's even correct. So let's go ahead and try. Now the question is, how the heck can we get the lifetimes to be different? Because the quality of the lifetimes, the lifetime doesn't depend on how you measure. There's a unique lifetime, and that's kind of basic quantum mechanics. So let's look at what we actually measure with more care. We have the measurement of the beam lifetime was done by taking the rate of decay, so the slope, right? In which we look at the number of protons observed per unit time, and we normalize to the number of neutrons that come into the beam. Now, if you're a little careful in this, you'll notice that, of course, the number of protons that you're observing is the number of neutrons that are decaying times the fraction of the neutrons that produce a proton in the decay. And then this factor, this number of neutrons decaying per unit time in units of the number of neutrons that you start with, is what we call the lifetime. So this lifetime, this number of neutrons that are decaying per unit time, is what is measured in the bottle experiment, because you start with some number of neutrons and see how many neutrons you have at the end. And normally, you expect the branching fraction, the number of neutrons that go into protons, to be 100%. So this would give you equality between the beam and bottle measurements. But if for some reason this branching fraction is less than 100%, then you can have a situation in which the bottle lifetime is smaller than the beam lifetime, as it is observed. So this was actually the main observation that Bart and I made, that the beam is measuring only the protons, and so we proposed that that the explanation lies in the fact that the neutron decays into a proton 99% of the time, and the other 1% of the time it produces something else that the experiment doesn't, the beam experiment doesn't see. And that means that the neutron could decay into other standard model particles that are not including protons, or that the neutron would decay into standard model particles plus some new particles that we don't know of yet, some dark particles. We don't know them because they don't have charge. Anything that doesn't have a charge we want to call a dark particle. Or maybe the neutron just decays purely into dark particles. And of these possibilities, the first one is ruled out right away because in the standard, as we'll see right away, if the neutron decays into standard model particles through some new interactions that we didn't know about yet, but if you presume that exists, if that happened, then all nuclei would be unstable, and the lifetime that we're talking about, 15 minutes divided by 1%, corresponds to about 1 day. So the typical lifetime of nuclei would be of the order of 1 day. That would be very bad news for civilization, or for mankind, or for anything. So that's ruled out. And let me kind of explain where that comes from, because it's influential also in understanding the other two. Well, if you propose something as radical as this idea, the first thing you do is go look at the particle data book. If you're a particle physicist, that's what you always do, to see if there's anything known already about, say, the neutron decaying into invisible particles, invisible end products. And, you know, remember, we're proposing that this could happen with a lifetime of 1 day or so. And the first entry here says, well, the neutron to invisible lifetime has to be bigger than 10 to 29 years, which is a little bit larger than 1 day. So, so to get around this, you have to understand where this comes from. And this bound comes from looking at oxygen. It's really huge tanks of water, which of course have a lot of oxygen in molecular form, that look for photons. So the water acts as a Cherenkov detector itself, and the idea is if the neutron disappears from oxygen 16, it gives you oxygen 15 with a hole, so it's some sort of excited version of oxygen. This in turn relaxes to the ground state of oxygen and emits a photon. And by not finding these photons, you can place a bound on the lifetime of the neutron. So in our case, what we want to do is say, well, suppose that the oxygen, or in this case beryllium, I explain why in a second, goes into de-excites by emitting a neutron, well, by the neutron transforming into some dark final state. And what we want to argue is that this dark final state is sufficiently heavy this process won't happen, even though the neutron in empty space can decay into this final state. So I'm going to do this with beryllium because beryllium-9 turns to give you the strongest bound. So if I manage this, then oxygen is also covered. So think of this vertical axis as energy. And say, and remember, mc squared stands for energy. So the mass of beryllium is energy. So remember, for a particle to decay, the final states have to have the sum of the masses of the final state have to be smaller than the mass of the initial state. And what I'm showing you here is here's the mass of beryllium in this simple figure. The mass of beryllium-8 plus the mass of the neutron, the free neutron that I would have if I separate them both by hand, is above the mass of beryllium-9. And I put that in there because this separation is something that nuclear physicists know very well and measure very well. It's given by this quantity. It's called the neutron separation energy. But what matters to us is that we know this number. Now, if the mass of beryllium-8 plus the mass of the final state dark particle or particles is anywhere in this brown band, then the decay of beryllium-9 can occur. If, however, it is in this region above the dotted line, then the decay cannot occur. And we're interested in that case when it cannot occur. Now, it's very easy to see now that the difference between this number and that one is just the mass difference between the neutron and the mass of the final state dark particles. And clearly, we want this difference to be smaller than the distance between the dotted line and the blue line, this 1.664 MeV, in order to forbid the decay of beryllium-9. So that this difference is more than 1.664 tells us that the mass of the dark particle has to be greater than this number, 937.9 MeV. And I say it's smaller than 939.565. This is the mass of the neutron. So for the neutron to decay into the dark state, it has to be heavier. So this explanation is viable and consistent with the existence of nuclei, provided the dark particles in the final state add up to something in this very, very narrow range. In fact, the range is a little bit narrower because there's another decay channel that makes it a little bit narrower, but not really central to the story, but numerically a little important. So we're going to assume that there's a dark particle in that, or a collection of dark particles whose mass adds to that something in that range, and then we don't have a problem with stability of nuclei. Now, because these particles are dark and their masses add up to about a GeV, this would be a good candidate, perhaps, for dark matter, the dark matter that makes up the universe. I kind of make a distinction between dark particles, which are just dark, and dark matter, which is that which fills up, 25% of the universe. In fact, a writer from Scientific American said of this that the missing neutrons may lead to a secret life, as dark matter, which is very poetic, which is why we had this thing in the first slide. You see, it's a secret life of the neutron. But I'm not going to go into great detail there. I just want to see what other conditions come from that and whether this is at all feasible. So the dark matter has to be stable because it's still around after 10 billion years of existence of the universe. So it has to have has to be either stable or very, very long lifetime, let's say, like protons or neutrons. But in principle, since the neutrons can beta decay, then the dark particle can beta decay. You can think of it, it has the same quantum number of the neutron, basically. If since the neutron can decay into it, it could go do the reverse thing, at least virtually into a neutron and then beta decay. So to ensure that this doesn't happen, you can require that the dark particle itself be lighter than the mass of the proton and the electron. So this thing cannot, the mass of neutrino is negligible. And if the mass of the initial state is below the mass of the final state, this doesn't happen. And interestingly, this number is exactly halfway the window that I showed you before. So this is the lower end of the window that I showed you before. And this is this new edge of the window. And it's in this lower end of the window that this particle could possibly be stable. And then it would possibly be the dark matter. What we're going to be looking at, and I'll look at this in more detail momentarily, is a couple of scenarios which I kind of mentioned earlier, in which the neutron decays into one of these dark particles and a standard model particle, a photon or E plus E minus, or a scenario in which the dark particle in which there's only dark particles in the final state. I'm call them scenario 1 and scenario 2. And let me before I go into specific microscopic models of these to see if one can implement it, at this point we can already formulate hypotheses that can be tested experimentally. So very generic, very model independent test of whether this assumption that there's a dark decay possibly is the explanation of what's happening. You can do this both in beam experiments and in bottle experiments. So here's two of the ongoing beam experiments. One is in Colorado, the U.S. The NIST Center for Neutron Research. So NIST stands for National Institute for Standards and Technology, and then J-Park in Japan, which also houses KEK. The test that you can imagine is, well, if this is not an instrumental issue, you could extend the length over which you're measuring the decay in the beam experiment, or you can have several segmented regions of decay and actually measure the shape of the exponential. So the shape of the exponential, even if you're just looking at protons, should give you the actual lifetime, the same lifetime as a bottle experiment. So measure the protons in the decay, but see that there's an actual that the exponential, not the rate of protons instantaneously, not the rate of decay into protons instantaneously, but the exponential that is traced over length of the experiment gives exactly the same as the bottle experiment. So that's the first thing one can do. The bottle experiment can do the opposite thing. In a bottle experiment, you're counting neutrons as you spill them, but you can actually imagine inserting a detector inside the bottle to count protons as the neutrons are decaying and check that the number of protons that you get is smaller than the total number of neutrons that are decaying that you measured. So some of these things are actually being planned, and that, as I said, if nothing else, we have contributed to this discussion by keeping the experimentalist busy. Okay, so let me give you a quick rundown on microscopic models. So to make sure that this is a viable idea, can you actually implement it somehow? And again, I'm going to concentrate on these two types of models: dark particle plus photon, or two dark particles. So in the idea is I'm going to have a neutron well, a neutron that goes into a dark particle for a photon. I guess I wanted to, because I'm going to show you some experimental tests of these. The photon, this is a two-body decay, so the particles in the final state have fixed energies, if you know their masses. Since the mass of the dark particles in this range that I showed before, the photon energy has a range that is fixed, and then the range of energies for the photon that corresponds to the case where the particle could be the dark matter, which is the lower half of this mass range, is the upper half of the photon energy range. That will play a role momentarily, so just keep that in mind. Okay, so here's the model. It's very simple at the level of nucleons. Neutrons have a magnetic moment, so they interact with photons. You can imagine having an interaction that gives you a small amount of mixing between the neutron and the dark particle. This is a mass mixing. If I put these two diagrams together, voila, out comes something that looks like a neutron, goes into a photon, and a virtual neutron, which then becomes the dark particle. Or you can go into mass eigenstate basis, and that just becomes the thing that I started with, that I wanted to get to. If you want to see equations, because people like equations, here's the magnetic moment of the neutron. Here's the mass term for the chi particle and the neutron. And this is the mixing term. And if you then rotate to a mass eigenstate basis, you get a mixing term. And I wrote it down here with it's a transition magnetic moment term, technically. So epsilon here is important. That's this thing that parameterizes this mass mixing and gives rise to the effect. Now, you can actually compute. You can say, if I want this effect to be 1%, then what parameters should I take? So if x here is the ratio of masses, and x is in this very narrow range, very close to 1, then you reproduce the 1%, if this parameter epsilon has a ridiculously small number. In units of GeV is 10 to the minus 13. And this means that we can produce this, as you'll see momentarily, with very, very short distance new physics, which means that we don't have direct evidence or direct test of these from collider experiments. And to show that, so this shows you that at this level it's a viable idea, but you know that neutrons are made of quarks, and so we should actually put this in terms of a more fundamental theory. And I don't want you to look at the equations unless you're a particle physicist. You can easily make up a model that does what we want by adding to the standard model a single particle. These particles have been studied to death in the literature. They're called diquarks. There's a scalar, so it's a spin zero boson that couples to a pair of quarks up and down. So it carries exactly the same quantum number as an anti-d quark. So we assume that this exists with a coupling to the two quarks. And then we assume that there's a dark particle, of course. And then there's this diquark has the right quantum number to combine with a down quark and produce the dark particle. And then the photon, of course, gets emitted anywhere. You should think of this as the magnetic moment of the neutron. So it's this interaction that produces that effect of mixing of the neutron with the dark particle. And then this parameter epsilon that we talked about before can be computed in terms of these couplings of that vertex and that vertex, which are labeled here by lambda. This thing also depends on the mass of this particle, which we call m phi square. And then beta is a computable quantity in quantum chromodynamics. And if you plug in the numbers, you find that this mass of this particle, well, modulo the value of these couplings that we don't know, is very large. 400 TeV is the same as 400,000 times the mass of the proton. So this is very far from where collider experiments are now. Of course, if these couplings are small, then this mass could be within the reach of colliders, so you can search for these. And given the time, I'm not going to go through this slide in any detail, but these slides exist, these searches exist, and basically tell us that the mass of this particle has to be bigger than about 1 TeV instead of 400. So there's a lot of ground to still cover here. So when we did our first paper on this, only paper on this, I guess, we got calls immediately from people doing experiments, and they wanted to test this idea that a photon is produced. And within a few weeks of our paper, the experiment was done, which is mind-boggling for people who do particle physics and have to wait 20 years for any experiment to actually appear. So 2 weeks later, this UC and A collaboration put out this paper where they put a 2.2 exclusion on these hypotheses that I talk about for energies in the band between about 800 keV to 1600 keV, which is where they have sensitivity. It also happens to be the energy band, with, as I showed you before, where the dark particle could be a dark matter particle. So 2.2 sigma exclusion is not the strongest, but it's indicative that maybe that's not the right explanation. I didn't talk about E plus E minus. Those, we don't have a good theory for that anyway, but those you can be much more sensitive to, and that can be ruled out with high level of confidence down to some energy, and then below some energy they don't have any sensitivity. So again, for non-dark matter type explanations, it's still viable. And other experiments have come into the fry, and I'm not gonna, and the results are consistent. So very briefly, you can do this also with, you can also have models where the decay goes into 2 particles. This part of the model decided before, now I call this thing chi tilde, where chi tilde can be, for example, heavier than the neutron, so the neutron cannot decay into it. But it itself can go into particles in the dark sector, say a pair of particles like I show here. And then you have a purely dark decay. And in this case, the kind of bound that I had before was, of course, that the masses have to add up to be in the range that I showed you. And the dark matter case corresponds to when the mass difference between these two is below proton plus electron. And I'll run through this because of the time, but the mass in this case is can be estimated. It's a little bit of a different estimate, but the result is similar. You know, that the mass can be as large as 1600 TeV. So again, it's not directly measurable. You can have a situation where this chi tilde particle is slightly lighter than the neutron, in which case 2 things could happen. Either the neutron goes to chi tilde plus photon as in the first model, or you can just directly go through this diagram into 2 dark particles. So the 2 of them had to add up to 1%. So you can construct models like that. Okay, so David, how am I doing with time?
I mean, it's 1, but you can continue. You have as much time as you want.
Okay, well, I'm going to try to not go over time a long time. We did start a little late. There was, as I said, there's other topics I can cover. I prepared very little material for this because I knew I was going to be short on time, but I do want to talk about the first one, which has 2 or 3 slides. Which I want to talk about that one because it's exciting to me, and it's still evolving. So I showed you before that the stable nuclei remains stable if the mass of the dark particle is above the mass of the neutron minus the separation energy of beryllium. And it's a little stronger from this. Well, never mind. That's what I showed you, right? This doesn't mean that there aren't other nuclei with smaller separation energies, which would make these more stringent. However, beryllium is the stable nucleus with the smaller separation energy. We could have dark decays of unstable nuclei if the mass is in this range and the unstable nuclei have smaller separation energies. So if the mass of the dark particle is below the mass of the neutron, take away the separation energy of those unstable nuclei, then of course those unstable nuclei are unstable, but they will have some fraction of the time they will decay in a dark way. And that's interesting because you could actually kind of look for the production of these dark particles in the decay of unstable nuclei. So an example of that, so Bart and I are not nuclear physicists, but we can dig into nuclear physics tables. So we saw, lithium-11 has a fairly small number for the separation energy, neutron separation energy. And we proposed that lithium-11 could go into lithium-10 plus a dark particle, and then lithium-10 actually decays into well-known final states, which could be searched for. But professionals, meaning nuclear physicists, pointed out that a much better candidate is beryllium-11, not beryllium-9 that we talked about before, which is stable. Beryllium-11 is unstable, which could go into beryllium-10 plus the dark particle, which then, this is the chi-til that I showed before, which was into chi-phi. So a dark decay of beryllium-10. And the separation energy of beryllium-11 is just a little higher than that. It's 0.5, but certainly much more than 1.5. So beryllium-11 can decay into boron-11 by this is a beta decay, or it can go into lithium-7 plus helium-4. So that's that process. And this is roughly the dominant branching fractions. Given that we know the parameters for our dark particle couplings to the neutron, you can estimate the decay. Well, I'll get to that. There's theoretical estimates for one tiny process, which is called beta delayed proton emission. And beta delayed proton emission means that the beta decay into boron goes into an excited state of boron, which then decays into beryllium-10 plus a proton. And because the first step of this is weak, it's called delayed. And the estimate is that this branching fraction is 2 times 10 to the minus 8. And this was interesting to some people because boron-11 is what's called a halo neutron, a halo nucleus. And beryllium-11 is a 1 neutron halo nucleus, which means that you can calculate. It's like you have basically you have a single neutron in a very outer shell, and you can control calculations better. I just showed you that the expectation was that 2 times 10 to the minus 8 for the branching fraction. Experiment was made in 2014, and it was found that the result, 8 times 10 to the minus 6, is 400 times larger than what was expected. Now, the people who made this measurement proposed, and also had made the theoretical prediction of the branching fraction, proposed that, well, they didn't know what was the origin of the discrepancy, but one possible explanation was the existence of a new resonance in beryllium-10 that would in boron-11, sorry, that would that would enhance the decay, and they even actually calculated how large, what the resonance mass had to be. It has very narrow range. We're looking for something above this line here. So to get to the branching fraction of 10 to the minus 5, basically, the resonance energy has to be kind of in this range, and the width has to be tiny. The width for that resonance has to be at most like a keV or something like that. Well, if you look at the levels of boron 11, there isn't anything there. And also the widths of the states that have been seen in above, some much lower energy are very large compared to 1 keV. And that's because all of these decay strongly. The small widths here are because the strong decays are forbidden, and those are just electromagnetic decays. They're narrow resonances. So that's one thing they proposed. And the same authors came back 2 years ago and said, well, look, if this dark neutron decay can happen, then that could explain this old observation from 2014. And they actually, this is a plot from their paper saying the branching fraction, all of the parameters are fixed except the mass of the dark particle. As a function of the mass of the dark particle, the branching fraction has this shape, and 10 to the minus 6 is at that point, which is perfectly consistent with the window that we were talking about, this of mass. So that they propose that's a possible solution. So this is very exciting, but we want to have some sort of confirmation of these. And in particular, are there protons in the final state of the beryllium-11 decays? So these measurements only looked for, let me go back, they look for beryllium-11 going to beryllium-10 through these beta delayed proton emission, but they don't look for the protons or the electrons. They just look for the beryllium-10. So if the dark decay is the explanation, there should be no protons. So this would test all channels for these dark decays, at least in this mass range. So this is very exciting, and there are several experiments that can do this. And in fact, these same authors are carrying out an experiment at CERN. Now, there's an experiment at Triumph was made, and they claim to find protons in the final state, and they find a branching fraction which is consistent with what was found before. So that sounds like bad news. However, this should be an alpha, not A. The CERN experiment found that there's a huge amount of background from alpha particles, and described how this result is most likely due to alpha particles. So this is at present debated. In the meantime, an experimental theoretical paper suggests that there might be a narrow resonance in around the region that is of interest. Of course, these calculations are very tricky. So this is an interesting story, and it's ongoing. Okay, now as I said, I'm going to spare you the details of the other slides, except for one. These couple last slides on other solutions. There's other people who have proposed other solutions to this neutron lifetime puzzle, or other models. There's a neutrino mode for that I didn't talk about, which is interesting in its own right, but I won't mention it. Let me go from the bottom up. There's a mirror neutron rapid oscillations that were proposed. There's mirror neutron oscillations enhanced by large magnetic fields. And there's a proposal that there's no problem, basically, that the measurement. So this proposal was very troubling, that the measurements of the lifetime of properties of the neutron, together with theory, are consistent with the bottle neutron lifetime and not with the beam. So the beam lifetime is incorrect. So this is my last slide. The standard model can be predicted in terms of two parameters. This mixing angle, which is fairly well measured by from nuclear decays, although I think the errors are underestimated, but that's my personal view. And then GA, now for the concentric, GA is the axial vector current. This GV should be in here, some mistake, and it's measured. So if you measure these two parameters, you can predict the neutron lifetime. And if you use the PDG value for GA and for CKM for VUD, you get a range of values which exactly spans the two measurements. This is very close to the bottle to the beam measurement. This is the bottle measurement. So this doesn't help. You can try to use a lattice result for GA. It's the best result in the lattice is this, very accurate, but not accurate enough. Or you can use experiment. And this is the situation as of about now. These experiments are fairly recent, late 2019. The blue experiments use one method, use electron asymmetries. The red experiments use a different method in which the neutron decay proton energies and angles are measured. And the two most recent and most accurate measurements, one of them gives almost exactly the bottle value for the lifetime, and the other one is right smack at gives right smack the beam value for the lifetime. And these are the values as a function of GA. This lambda parameter is the same as GA. So this is an ongoing, unfolding story. I don't know what the end result is going to be, but we certainly have had a lot of fun. And I really thank you for your patience. I went over a little bit. And I will leave you with this quote again from that Scientific American article, which again is very poetic. Thank you very much.
Thank you, Benjamin, for your interesting talk. We already have some questions from the public. I remind you, if you want to have a question, try to use the raise your hand button. If you cannot do it, then you can tell me, send me a message, or turn on your microphone if you cannot do it. So now we start with a question from Pablo Roig. Adelante, Pablo.
Thank you. So can you comment on the possible implications of this explanation with respect to unitarity of the U-quark couplings, and also, if possible, related to explaining the baryon asymmetry of the universe?
Okay, so thanks for the question. Very interesting. So the unitarity, I suppose you mean the unitarity of the CKM matrix, the mixing matrix, right? So the mixing matrix is not modified at all because the weak interactions. So this diagram that I have here is perfect for that. The new interactions that are required for this to work do not modify the weak interactions, and do not affect the mass matrix of the quarks themselves. So the description of the whole process of diagonalizing the mass matrices and therefore putting the rotation matrices into the couplings to the W, which are the CKM matrices, is exactly as in the standard model, and they remain unitary. As for your second question was on baryon asymmetry of the universe. Since the some people have looked at this. Let me see if I have something here. I don't think I have. Yeah, I don't have anything here. It's kind of interesting that you can assign baryon number to these particles because, as you can see, the neutron in the initial state produces one of these particles or a collection of these particles in the final state. So baryon number is conserved if you assign baryon number to, say, these chi particles, these fermion particles in the final state, to be the same as that of the neutron. And some authors have commented on addressing well, the baryon. Sorry, let me take a sip of water. So I want to try to do two things at once. So the baryon asymmetry, just plain baryon, explained through standard dark matter thermally produced, and doing on the for baryogenesis whatever you wanted to do before in your model. The baryogenesis directly. That, you know, and we don't know what generates baryon number. However, I guess I'm going to run a bit in circles. What people have addressed is, if you take a model that has baryogenesis, because these objects have baryon number, you can try to address this question of the what's called the coincidence problem. Why is it that the dark matter density today is so similar to the observable matter density? And that has been done, I think, in some papers. But that's just building up on similar ideas that already existed, so it's not really novel. So I don't know if if that's a satisfactory answer, but as I said, this model doesn't have ingredients that that address baryogenesis. It does address kind of automatically dark matter production.
Thank you very much.
Mm-hmm.
Thanks for your question, Pablo. Libertad, you can turn on your microphone. Go ahead.
Yeah. Thanks, David. Thanks for this very interesting and nice talk. I mean, I have a short. There are perspectives to perform in the near future experiments where they determine the neutron lifetime with the two methods simultaneously. I think they want to do bottle experiments, but detecting with scintillators the protons from the beta decay, and I guess that's something that many people are expecting in order to get a solution of this long-standing puzzle.
Yeah.
And I think you mentioned that there have been other. You mentioned briefly that there are other proposals that came up, like regarding possible decay channels, exotic decay channels for the neutron. Can you maybe comment a little bit on that?
Yes. So the other proposal that is this one in particular, where the neutron. So of course, other than the dark channels, in which the different final states don't really mean much because they're dark. The proposals that are interesting is what you include standard model particles, there's of course the possibilities. There are only so many possibilities because there are a few particles that are lighter than the neutron in the standard model, and so E plus E minus is one possibility, but it's fairly the bound is fairly stringent already these existing UCNA experiments and others. And so these other case that I had in mind is this Neutrino Mode, which doesn't help you much as an experimentalist because it's not easy to see neutrinos. But the proposal is interesting because the parameters and the way in which it is built is different, and there's other ways to get at it experimentally. So in this model, the idea is to have some sort of a vector particle, like a z, it's called a z prime, that can then turn into a neutrino-antineutrino pair, just like the z of the standard model. The problem with that, of course, is the neutrinos are always partners of the electrons in the electroweak theory, and we can get around that. So if the z goes into neutrino pairs, they can also go into E plus E minus. So the idea there was that you can suppress the rate into E plus E minus relative to the one to neutrinos very dramatically, just from the available phase space. And this is a really bad plot that was supposed to show that. But so this model is kind of interesting because it still allows then for the possibility of E plus E minus precisely where the energy is low for them, where they haven't been searched that well, and the rate will be very low because they're competing with the decay into neutrinos. And in addition, you can actually kind of reverse the process, and instead of producing an E plus E minus in the final state, by crossing, put the electron in the first state, and by looking at electron-neutron scattering, you can try to search for electron plus dark particle. So that's the other channel I had in mind. Is that?
Yes, thank you. Thank you.
Thanks, Libertad. Miguel, go ahead.
Thank you for the talk, Benjamin. So if related to the paper that you showed from Marciano, Sirling, and Czarnecki, so if we compare these, the preferred values for the neutron lifetime from this standard model prediction and the one from Bodel experiments, so the decay of neutrons to exotics should be at the level of 1 per mil and not at the level of 1%. So my first question is if this is still interesting for the models you are considering. And the second is that if a neutron beta decay rate can be measured directly, at least in Bodel experiments, because this would allow to test the standard model prediction for beta decay. I think at some precision that could be competitive with Fermi decays.
So I'm not sure I understand your last question, whether neutron beta decay can be
if neutron beta decay can be measured directly, because we usually assume that the neutron lifetime is the inverse of the neutron beta decay rate.
Right.
But this is not a direct measurement.
Okay, so in the talk, I reported that, and Libertad actually just mentioned it too, right? That experiments, particular Bodel experiments, are now trying to put into the Bodel itself detecting devices like, well, let's not get into the technology that can directly measure the the outgoing particles in the decay. For example, protons or electrons, and typically protons. So that is happening. Now, with respect to your first question, you made the wrong statement that that the lifetime by this formula only gives room for about 1 per mil deviations from the neutron for the neutron to decay as in the standard model. That is true if you use the value from the Perkeo collaboration, which is indicated here in blue. However, if you use the value from the more recent aspect collaboration experiment, you get a value which is exactly, the central value is remarkably on top of the bottle experiment. Sorry, the beam experiment, I said it wrong. The Perkeo gives, so yes, this one doesn't give much room for the for the beam experimental result to be consistent with theory, but this other one doesn't give any room for the bottle experimental result to be consistent with theory. And these two are in tension with each other at almost 3 sigma. So I don't think that is resolved, and I don't think that is known. And I think you know, in my view, the right way to look at this is there's several tensions here. This increased intensity in experiment and theory is what is required to sort it out. But I don't think it's actually productive to say we don't have to do anything because the standard model is right, and let's take let's select from the measurements that one that suit our purposes. That may be right, but I don't think it's the right way to do science. And I think to some extent that's what Czarnecki, Marciano, and Celine do. So those of you who've never seen their paper, they classify measurements by those before 20. I can't remember, 2010.
22 for GA.
Right, 2002, is that what it was? Or 2000
yes.
or something?
Yes.
So the ones that are earlier are dismissed, and these ones that are later are kept. So of course the PDG doesn't do that. The PDG takes all values. But you see this tendency to go from right to left here. And if you keep these measurements, you get something more consistent with that. If you get these measurements, you get something more consistent with this. And they say, well, let's just ignore this. That's the content of their paper. And okay, if you want to do that, and you want to ignore also this one, the newest measurement, well, you're right. And look, I have to say this. I mean, some theories have been very successful at breaking new path by understanding what should be ignored and what should be kept. So notably, when V-A was discovered in the 50s, theorists, including Feynman and Gell-Mann and others, recognized that the solution for the problems at the time was that some experiments were incorrect. The experiments suggesting that that the interactions of atoms were scalar and tensor, as opposed to V-A, had to be incorrect because the theory convinced them that it couldn't be the case. And they just decided to ignore the experiment and force a reevaluation experiment. I think that's great, but I can't do that here. I don't know that I know enough about the systems to say, yeah, let's just ignore all of these other experiments and stick with these ones. So that's my view. I mean, it's my personal view, and you're welcome to your opinion.
Okay, thank you.
Thanks, Gabriel, for your question. We have a question from Armando Ulises. Yeah.
Thank you very much. Can you hear me? Yes.
Yes.
I have two questions. I have two questions. The first one is, if these dark particles exist, what should be the value of their spin? And the second question is, could it be possible to measure them via gravitational interactions, or it would be so difficult?
Okay. Thanks for your question, because I actually didn't explain that, although I should have. So the just from let me see if I have the other picture here. Sorry. So the fact that the neutron, which is a spin-and-a-half particle, through this type of explanation has to produce a particle plus a photon, where the photon is a spin-1 particle, tells you that these, just from angular momentum and addition of spin or J, that this particle has to have a spin either 1/2 or 3/2, which is 1/2 plus minus 1, right? Or 1 plus minus a half. And you know, as some people in the audience would be able to tell you, like Salim, making theories of elementary particles with spin 3/2 is not easy. So the natural thing to do here is to choose this particle to have spin 1/2. And that's the direction we went in. So again, this is somewhat model dependent, and the models that we investigated had these spin half particles in the final state. But in principle, it could be something that could be like spin 3/2. It could be that they're not fundamental particles, they're composites of something else in this dark universe that coexist with us. The other case with two dark particles, then again, the spin of these two together have to add up to, say, a half. And what we do is we choose this particle to be spin 1/2 and the other one to be spin 0. So again, that's a choice of how we implemented the model. And it could be more general than that, but it's in many ways these are the simplest choices. So I hope that addressed your first question. Your second question was about gravitational interactions, and so directly observing these through gravitational interactions, I think, would be challenging, if not impossible. However, if they are in fact the dark component, if they are a large component, if not the principal component of the dark matter that makes up the universe, or 28% of the energy balance of the universe, then they have been observed and through gravitational interactions. But of course, that's a big if. We don't know. So I would actually go the other way around. If we could establish that these particles exist, and we can also establish that they're stable, or at least that they have, they are in the mass range where they would be stable against beta decay, as I said, then it will be one of the very viable candidate for being the dark matter of the universe, and I think further study would be granted to try to establish where it is. And in that, if it did, then you could say, aha, they have been seen gravitationally a long time ago, although we didn't know that it was them. I hope that makes sense. Yeah.
Okay, thank you very much.
Sure.
Thank you, Armando. There was another question, but I think he regretted. So, well, maybe I can just finish with a question about the future of the field. I agree with you that it's a good research field, and I'm very happy to learn about this discrepancy that can give us a more understanding, right? Even if in the end there's no discrepancy, we're understanding more things. But I want to ask you, what do you think is the result, or what will happen in the field in the near future with this discrepancy between the two models? Like, the new experiments will tell us definitely if one of the experiments was wrong, or can exclude more conclusively some of the, for example, the simplest models?
Very good. I think I have at least partial answers to both of these. The first and most pressing question is whether there is a lifetime puzzle at all to begin with. And as I said, I think all eyes are now on this experiment at J-Park in Japan, the beam experiment, which is promising to have the smallest errors ever in that type of measurement, and for which the systematics are different than the ones that other experiments have contemplated before. So it's a new experiment. It may do away with the discrepancy and may confirm it. So that's I think the first step. And let me add something, since you're a captive audience, you have to hear this now. One of the things that I didn't explain this, but the last of the bottle experiments, well, there were two that were simultaneous, but one of the two latest experiments was an experiment that was very different from all of the previous ones. So one of the concerns, the main concern with the bottle experiments, is that no matter how hard you try, you might be losing neutrons by absorption into the walls. And so you try to correct for these, and there's many ways of correcting for these. And of course, if you lose neutrons, you get a longer lifetime. So it would go in the direction of catching up to to the bottle, to the beam experiment. You get a longer lifetime. You correct for that by subtracting, and then you make a mistake, right? So the latest experiment was a Los Alamos experiment, where the containment of the neutrons was done magnetically, and there was no contact with the walls at all. And that's the one that has the biggest discrepancy with the, right? It has very small error bars and has the biggest discrepancy. And that was what got us started, because everybody was hoping. Nobody thought there's a problem with the beam experiments. Everybody thought it was the bottle, because they can't control this very well, and they over subtract, and that's the problem. And then out came this experiment, which was going to clean everything up, and it just made it worse. So that's what I'm saying, that all eyes are now on the beam side, because of the bottle side. I don't know that anything much else will happen. Now, there's these experiments. I guess Dad mentioned also that putting detectors inside bottles, and the people doing the beam experiment in J-Park have talked about, we've had some informal conversations about doing this thing where you try to measure along the beam line to get an exponential decay. So those things are, those types of experiments are very important, I think, and they will happen. We just don't have a very good timeline. They're very important because, again, they ask a question at a very general level, which is not model dependent. And the third type of experiment that I think is very important that can shed some light is these decays of unstable nuclei. I think that thing is in a bit of disarray. And I really should actually do a bit more homework by talking to the people who've done these experiments and are planning. The most credible people in that field, in my view, are these Riesiger and Putzner, who I quoted in my talk, who are doing this experiment at the SALT in CERN, who recognize that there are very important difficulties in measuring the protons because they get these alpha particles, and published a partial result and never went around to publishing the final result. There must be some problems or some surprises or something, so we don't know. But those experiments, I think, are the most interesting because the class of experiments, these unstable nuclei, because you actually get to see a different system other than the neutron, where you can see the kind of directly see the dark particle in the sense that it always gets produced with something else that you can go after. So I think that's the direction. I think on the theoretical side, the direction is not really direct. I think Yael mentioned or someone, Pablo. Somebody mentioned the unitarity of CKM. There's actually problems with the unitarity of CKM, and there's problems with the calculation of the well, that may be due to the extraction of, for example, this mixing out of BUD from super allowed beta decays, which, as I said, is oversold. And I think there's a lot of interesting directions to go there. And in particular, I know that people are redoing calculations and trying to find new methods for calculations. People on the lattice are trying to do some calculations of those processes. So I think that's more the direction in which theory is going. I don't know if that's helpful, but that's my 2 cents.
Thank you. Well, if you allow us, now that you're a captive speaker too, we have one last question. Omar, go ahead.
Yes, sorry, we have to go for lunch. The thing is that with these reactions that you have described to produce dark matter, does it mean matter to dark matter is fixed, or does it changes as the universe evolves?
So it doesn't require that the ratio of baryonic matter to dark matter be fixed, but people have actually tried to construct models where it is fixed. Because that's a question that a lot of people have in their mind. It's called the coincidence problem. You probably know this. The coincidence problem is the problem of explaining why is it that the density of dark matter in the universe is so close to the density of observable baryonic matter in the universe, and you know, this question was raised maybe a decade or more ago, and people came up very creatively with solutions where basically the dark particles, the dark matter, carries baryon number also of some sort, so that when you create baryons, you also create dark particles, and if the masses and conditions are chosen correctly, you get a fixed ratio, and you just choose the parameters so that the fixed ratio is around 5 and you're in good shape. So that was actually done and realized quite a while ago. And then people more, you know, in the context of these type of questions, this neutron dark decay, people realized that you can get away with implementing some of those ideas in this context. So it's not necessary, but you can do it.
Okay. Thank you.
Sure, pleasure.
Thanks, Omar. Well, I'm sorry, Benjamin, but Gabriel has another question that he wants me to ask you. What do you think the UD nuclear decays is oversold?
There is a so let me say a few words about this. So you know that these super allowed transitions are supposed to be very good for determining VUD because the matrix elements in the calculation are model independent or solid under in calculations because in the isospin limit they're fixed at least at zero momentum transfer. The problem is that so I'll tell you why I think they're oversold because the isospin is good to, depending on the process that you look at, 1%, 5%, something like that. So that we say that we can compute these accurately because of isospin is a statement that should be understood as, provided you don't need accuracy better than about 5 or 10%, then you can trust this. So how is it that we say that we have an accuracy of better than 1 per mil? It's a fraction of 1 per mil that is quoted. If isospin only guarantees 3%, 5% accuracy, something like that, you have to get a factor of about 100 increase in accuracy, or at least 30. So now you go and look at the literature and see the calculations, and lo and behold, the calculations depend on using specific models for the nucleus to get the isospin breaking effects, which come from the mass of the quarks and the electromagnetic effects. You need to model the nucleus with your favorite model. Typically the shell model, but whatever you want. And many authors have done this. And then you look in your model at the prediction for VUD as a function of which nucleus you're using, which it should be universal, of course, and you get fairly large variations. Except for one group. There's one group that does this calculation. I can't remember the names, but I can look them up for you. But I think they're from the United States, I think from Houston. But the name escapes me. Which somehow very consistently gets all of the values to agree for VUD, regardless of which nucleus. And in fact, it's one of those remarkable things where when you put in all of the error bars, everything is way more consistent than you should expect, given that you understand what statistical fluctuations are. So the fact that it's one group out of so many that gets consistency, that they get it to be over-consistent with respect to these statistics, to me makes it troubling. But it's that result of that group that is quoted to do all of this. I'm an outsider, and I'm old, so I don't risk much, and I can speak freely, and I've said this in other conferences, and I think this thing has to be reevaluated. I'm sorry I forget the names of the people who I'm quoting. It's a little unfair that I don't remember, but I can certainly get the references for you.
Thank you very much for your answer. Well, we have one more question. I hope it's okay.
Yeah, sure.
Yeah, Andres, go ahead.
Hello. Okay, I know that we are searching for a dark matter particle, and recently we had found in some data in the LAC, and this data show that there are some evidence of dark matter. So when we were when we were studying this data, it was possible to identify some patterns of dark matter in the LAC. Okay, so I was listened your talk, and for me this model is very from the nuclear physics. So maybe I can be wrong, or this model we can show this model from the QCD. You got? Oh, this model is from QCD, or?
So are you asking whether this model is from QCD? The model of the neutron is from QCD. The model of the neutron is that it is made of quarks that are bound together by quantum chromodynamics, by gluons. So I am making that assumption only when I try to write down a microscopic model to produce the interaction of the neutron decay into these dark particles. So precisely this picture that I have here with these kind of a heavy scalar and then coupling to quarks and whatnot, that of course does assume that the neutron is made of quarks and has a binding given by quantum chromodynamics. That was not necessary for the initial hypothesis or even for the description of the neutron decay. But it is my belief that, or our belief that quantum chromodynamics is the correct theory of nucleons that prompted me to insist in going one step further and investigate how I would account for this neutron decay at a more microscopic level in terms of the case of quarks. So that's the way in which QCD is included here.
Okay, why which kind of decays from QCD we can apply here to describe this phenomena? Because, for example, when the neutron, when you collide neutrons, I understand, for example, that you collide neutrons and you can get the neutron, the dark matter particle by missing mass technique. You reconstruct the events and you can detect this particle. So I have interest to know the others, how can I say, the others decays, because, for example, we can find other kind of particles. As you know, we are searching also for a graviton, Maybe in this case, we can find this particle. It is possible to find this particle in this decays.
So we as I mentioned earlier, we look at the possible production of dark particles in collisions of well, I show you the collision of protons, which is what the LHC does. I could have shown you the collision of neutrons. The results would be similar, except for the fact that, of course, protons can be produced with much more higher intensity, and we can go to higher energies, which is very valuable in trying to probe for this. And the bottom line is that the rates are tremendously small and make this virtually unobservable in collisions. And it has nothing to do with quantum chromodynamics itself. It has to do with the with the fact that this interaction is incredibly weak. So, the interaction that produces the neutron decay, which is a weak interaction, is weak to begin with. But in the case of the neutron, the rate of decay of the neutron itself, just the beta decay rate, is particularly small because there's very little phase space in the decay of a neutron to a proton plus electron. The masses are very, very closely spaced. And so you want to introduce a new interaction, or you propose a new interaction that produces this dark particle. And that process is only a fraction, of course, only a fraction of the time than the normal neutron beta decay. Then this new interaction has to be even much weaker than that of the weak interactions, of the standard weak interactions. So, so as a result, when you want to search for this kind of interaction in collisions through some sort of production mechanism, the cross section for that production mechanism is terribly small, and well below the levels that any kind of modern experiment is sensitive to.
Okay, for me it was a little bit, there is a contradiction because, as I told you, we have find data, and this data show us that there is some evidence of dark matter, and we have analyzed the data from the RAC, for example, Atlas detector. In Atlas detector, we have found this evidence of dark matter or patterns of dark matter. So, but anyways, for example, we see the symmetric, the symmetric, the universe, there are symmetry in the universe. What does it mean? For example, we can detect dark matter when we collide protons, or basically we can find dark matter in this way, because this way is in this way we have found evidence of dark matter by neutron star, but basically this reaction of decays occurs in the regimen of nuclear physics. This is my question, actually. This is my confused. This is my problem for understand this topic.
Yeah, I'm not sure I understand what your confusion is. I think that the fact that you may be seeing dark matter production in a collision experiment, like in Atlas. By the way, I don't know what RAC stands for, so it would help me to understand that. But the fact that you're seeing collisions at Atlas that may be interpreted as producing dark matter, that's fantastic. It's great news. If you have that, that's revolutionary, and I congratulate you. And that could very well be indicative of an interaction that of the standard model with a new set of particles that we didn't know of that are dark. It's unlikely to be this model, except that, I mean, I did show you a slide where I told you what the possible outcomes are if this type of model is correct, as dark matter, LHC signatures of dark matter.
Okay.
So if in fact you're seeing something like missing energy that comes with with jets and monojets and so on, then that could be indicative of this model. It could be something else. It's not clear to me why. I mean, I wish I understood you. Why you think there is an inconsistency or a problem here?
because the regimen of energy, you know, and when we collide particles, we accelerate particles at high energies.
Yeah.
And when we use, for example, beta decay, the energy is is less than the the energy.
But this is the wonderful thing about quantum field theory, right? That you can have a model like quantum chromodynamics or the Fourier model or whatever that describes physics at very low energy and also at very high energy in the same one framework. So here, look, I can show you a diagram. Let's just take this diagram and ignore the photon, ignore the dark particle for now. Just focus on this phi particle. This phi particle has color. Has the numbers of an anti-D quark. Because it has color, you can produce it two ways. In a proton collision, you can up quark from one proton and a down quark from the other, and they will collide to make this particle. Okay. That's one way to produce it. Another one is because it has color, you can pair produce it in gluon-gluon fusion. So two gluons can make a pair of this particle and its antiparticle.
Okay.
Now, once you have the particle, you can now look at these two vertices. It can actually itself then decay into a down quark and a dark particle. So that would be a jet for the down particle and for the down quark and missing energy for the dark particle. Or it can decay into two jets corresponding to these two quarks.
Okay. It's very similar to the proton-proton collision. It's very similar.
This is exactly what I'm talking about in this slide. And I'm sorry I went to it through too fast. And I know there's a lot of fast stuff to take, but it is exactly. I mean, now I understand what you're talking about. It's exactly the context of this observation.
Yes, exactly. Oh, yes, exactly. Okay, thank you very much. My question was answered. Okay, thank you.
Very good. Thank you.
So, bueno, a lo mejor me gustaría terminar, Benjamín, preguntándote si tienes algún consejo para nuestros estudiantes que están empezando con sus carreras en física, para que tengan una carrera exitosa como la tuya. ¿Qué te parece?
Gracias. Es la pregunta de los... bueno, hay un par de cosas que les diría. La primera es que hay que trabajar muy duro. Si quieren salir adelante, van a competir con mucha gente que trabaja muy, muy fuerte. Entonces, por más brillante que sea uno, brillantez por sí misma no es suficiente, hay que trabajar muy duro. La segunda cosa que les recomendaría es tratar de... Lo más bonito del campo es interesarse por las cosas que están saliendo y cambiando y cómo está evolucionando la ciencia. Una cosa que no es productiva y no los va a hacer... a llevar a tener éxito en sus carreras es agarrarse de un problema y seguir, como decimos a veces en Estados Unidos, hacer el problema de tesis el resto de la carrera. La forma de tener más impacto y para mí, personalmente, divertirse más haciendo el trabajo es reinventándose, ver qué está pasando en el campo, ver qué es interesante, dónde hay preguntas buenas y seguirlas. Entonces, cuando uno es estudiante es un poco temprano para eso, pero si tienen la oportunidad tienen algo así como digamos el Journal Club, entonces te juntan con los compañeros y discuten qué ha pasado, qué es nuevo, qué está saliendo. y tener intereses más amplios que estancarse en un solo campito, en un solo tema de la carrera. Esto que hice de Neutron es algo que nunca había hecho antes, no tiene nada que ver con mi carrera anterior. Y la vez pasada que estaba en el Simvestab hablé acerca de flujos de renormalización y soluciones estables del grupo de renormalización, que es pura teoría cuántica de campos. Y lo que estoy tratando de enseñarles es que lo que estoy tratando de recomendar es lo que yo hago y es lo que me ha funcionado. Entonces, espero que el consejo les ayude. Y tienen una cosa muy importante. Tienen que gustar lo que están haciendo. Tienen que ser un gusto y una alegría trabajar en esto. Si no les gusta, van a hacer más dinero haciendo doctores o algo así, pero doctores de médicos, no de física. Entonces, háganlo por el gusto y por el placer y métanle mucho tiempo y esfuerzo y reinvéntense con frecuencia.
Vale, pues, gracias, Benjamín. Ha llegado el momento de terminar nuestro coloquio. Antes de ello, les quiero pedir a los asistentes, si pueden, enciendan su micrófono y su cámara para que me acompañen a darle las gracias. Un aplauso a Benjamín.
Gracias.
Gracias.
Por tu tiempo, te tomamos mucho tiempo, pero bueno, te lo agradezco y yo pienso que va a ser útil también para los estudiantes que nos diste.
Fue un placer.
Vale.
Hasta luego.
Gracias.
Muchas gracias. Thank you.
Gracias, thank you.
Hasta luego.
La semana que entra, el profesor Maciek Sianowski de Łódź, en Polonia. ¿Vale? Hasta luego. Bye.
Hasta luego.
Gracias, David Bermúdez.
Gracias por venir. Bye. Nos vemos la semana que entra.
David, antes de que te vayas, una pregunta. Mencionados sobre la participación, que teníamos que hacer algo para demostrar nuestra participación. No vi dónde la colocaste para que sepan que estoy participando.
Envíame un correo, Lilia. Eres Lilia, ¿verdad?
Sí, así es.
Si quieres nada más con que me envíes un correo con eso, ya nos acordamos, porque como tú no tienes el correo del Simvestab, no puedes acceder a esa forma que le envié. Pero ya te vi que estás aquí, mándame un correo y con eso.
Ok, sí, porque ya les había enviado un correo de que necesitaba una constancia. Entonces, para que sepan que sí estoy aquí presente.
Vale. Sí, lo recuerdo. Vale.
Bueno, muchas gracias. Nos vemos.
Bye.
Bye.